We have started BGP, and we have seen that BGP uses path vector routing, which means that the routing information, the vector, contains not a cost, but the concatenation of all the domains that are used on the path. The domain are called AS, autonomous systems. They are given by a 32-bit number. And we have seen that, for example, E has gathered information about prefix N1 in the form of the path BA. That's our first important thing about BGP. Another important thing about BGP is how BGP is implemented. BGP is implemented by having BGP routers inside the network that is interconnected by BGP. So we don't have an intermediate router between. For example, here, D2 and D3, autonomous systems D2 and D3 are both using BGP. There is one BGP router in D2 and another BGP router in D3. The language, the protocol that is used between B and D is BGP. If we zoom on domain D3, D3 has 4 neighbors, so it has at least 4 BGP routers. At least in this case. Now, it could be that the same BGP routers has 2 connections, but in this case that is shown here, there is 1 BGP router per connection. So we have C, D, E, and F that are BGP routers. They speak BGP to the outside BGP routers. Now, they also need to pass inside their own domain the information that they have learned. For example, A will learn from D1 that there is a path to N1 that is D1X. B will learn from D2 that there is another path to N1, which is D2X. Now, C and D need to somehow share the information and pass it along so that global path computation is performed. For that, there is, between all BGP routers inside the domain, so R might not be a BGP router here, at least those 4 must be BGP routers. There is what is called a BGP mesh, which means that all BGP router inside the domain peers with all other BGP router inside the other domain via a TCP connection. So when C boots as a BGP router, it must know what are the IP addresses of all the BGP routers in this domain, and it will establish a connection to D, to E, and to F. Now this connection might be multi-hop. In the case here, perhaps the path from C to F is via R. In this case, R is not a BGP router. So there is a connection here that is 2-hop here. Between routers that are inside, BGP routers that are inside the same domain, the protocol that is used is also BGP. So BGP is used between domains and also inside a domain. When BGP is used between domains, it's called eBGP. When it's used inside the domain, it's called iBGP, interior and exterior. But be careful, those are not 2 different protocols. Those are it is exactly the same protocol. There is only one rule that applies differently in one case and the other. The rule for iBGP is that the most important rule is this one. Routes learned from a BGP router in the mesh, inside the same domain, are not repeated inside the domain. This means if D learns a route from B, it will repeat it to everyone. But if D learns a route from C, it will not repeat it to everyone. Which makes sense because we assume that C is connected to everyone. So if D has learned something from C, E and F should have learned the same thing from C. So this is the only rule that makes a difference between iBGP and eBGP. There is also another obvious rule, which is that when D learns a route from B, which is in D2, the route as seen from B is D2XN1. When D puts its route somewhere inside when, for example, B passes that information to D, B adds D2, its own domain, to D. Right? But when D passes this information to F, D will not add D3 because we are inside the same domain. That's an obvious rule. So the only important one is this one. For example, here I'm showing 3 potential updates from C to A, the route D3, D2X to N1, etc. Which of those routes are legitimate in BGP messages? Which of the routes can be sent if we apply the rules that we have seen so far? 5 more seconds and I close the poll. I close the poll now. And the majority vote is the correct one. The route 1 from C to A, D3, D2X, has been learned from C, C has learned it, very probably, D3, D2X from B, from router B, from router D. So this has been learned internally, but this is sent to an external peer, so that is okay. Same for this one, it has been learned internally by D. And no, sorry, it has been learned externally by D. So D has learned this directly from the outside, so it forwards it inside. This is correct. But this one should not be forwarded because C has learned this route from D. So it should not repeat it to E. Well, that's the first principle of operation of BGP. Another small question. Which of those 2 sentences is correct? 5 more seconds and I close the poll. I close the poll. Huh. So 1 is true. 2 BGP peers must be connected by a TCP connection. I mentioned that inside the mesh. It's also true across the boundary. So external BGP peers also use TCP to avoid having to manage packet losses. 2 BGP peers must be on link. This is not true. On link means they are in the same subnetwork. This is usually true for external peers, but is usually not true for internal peers. For example, here C and F are not on link. C and F communicate via BGP, but they are not direct neighbors, which means they use the interior routing protocol. They assume that the interior routes have been built and set up so that we can know how to reach F from C. So the correct answer is answer 1. Here, ASA, this one, is a stub. A stub means it's a dead end. It's the end of the internet. It's not a transit. When you reach A, in order to go somewhere else, you have to exit A by the same connection here. A is not connected to anything else than D here. Is it thinkable that instead of the diagram that is shown here, where A is interconnected using BGP, is it thinkable to avoid using BGP and still have routing that would work here? I close the poll now. Well, to be honest, it's a bit ambiguous the way the question is asked. Let's see exactly how things could happen. Let's do the game. Let's assume we want to work without BGP between A and the neighbor. What would we need? Well, we need first that all traffic inside A to the outside knows where to go. We can reach that with BGP. We will see how, but we can reach that in this case here in a simpler way because there is only one interconnection point from A to the outside world. It is A2. So all we need is a default route, which means, for example, A2 could insert in IGP, in RIP, for example, the route 0/0, that means the null prefix, the default route. So A says, I have a route to anything, and this will be passed along to all routers inside A. Then what's the effect? If there is a packet at A3, at A4, for example, that has a destination that is not inside the cloud, it will match only the 0/0, and the route to /0 will be computed using RIP. So I don't know about exactly the interconnection, but at the end of the RIP path, we will end up in A2. In other words, A2 does as if it had a prefix that is locally connected, that is 0/0. If we do this, that will work one way. Traffic from A to the outside world will know where to go. Is that sufficient? Well, we need also that traffic from the outside knows where to go. If I have something to a prefix that's inside A, we need that it knows where to go. For this, in principle, that's the goal of BGP. BGP will pass the information to D6, what are all the prefixes that are inside the cloud A. So if we don't do this, then we need that D6 injects into the routing protocol all the prefixes of A. For example, I don't know if A is a 16-bit prefix. If all the subnets in A are 128.178/16, for example, then it's possible, but we would require the collaboration of D6. We require that D6 injects this as if pretends that it is connected to N16. So if we do all those cheating arrangements, which means the correct solution is 3, if we do all those cheating arrangements, then it is possible to not use BGP. Is it easy? Is it not easy? It depends on the nature of the network A and of the IP addresses that are given to A. In the case of EPFL, for example, EPFL has a prefix of length 15, so N/15. Then this is exactly what is done. EPFL doesn't run BGP. It speaks to switch, and the first switch router, which is, by the way, at EPFL, injects into the switch network the prefix 128.178/15. And all EPFL routers have a default route to switch. It works even if we have several interconnection points. It's possible that each of the interconnection points injects those two things, and then the rest of routing will compute the shortest path towards the nearest interconnection point. So it is possible for some networks to be interconnected while not running BGP. But it requires some collaboration. Here it's typically done when D is a service provider for A. So we don't always need BGP. But now if we do need BGP, which is in all other cases, if you're not directly connected to a provider, or if you, not like EPFL, if you have 200 different prefixes that are likely to change all the time, then you don't want to statically configure in the provider network what are all the prefixes you have. BGP uses path vector routing, and I mentioned why. I mentioned this is, for example, because domain E does not like domain B. So when E is routing towards A, E would prefer not to use B if it is possible. This is called policy routing. So policy routing means that because interconnection is self-organized, all arrangements that are physically possible are perhaps not desired. For example, typically, you have different types of relations. A very common relation is customer-provider and peers. Customer-provider means one network is customer of another one, and peers means that they are at the same level. For example, internet service providers, typically. Let's explain in more detail on this example what could happen here. Here I'm showing 3 networks, 6 in fact. The blue ones are internet service providers, and the pink ones are customers. They may be big, but they are considered as customers here. And one internet service provider has presence both in the United States and in Europe. ISP3 has presence only in the US, and ISP2 has presence only in Europe. Right? So what we would like is to avoid cases like ISP3 might find it advantageous to send the traffic to N2, for example. If this customer sends traffic to N2, then ISP3 is connected to ISP1 and ISP2, but it's better for ISP3 to send it to ISP1 because they are peers, probably in the same city or even in the same building. They are both located in the United States. But ISP1 might not like this because ISP1 is a peer of ISP3. ISP3 is not a customer of ISP1. So the traffic that goes from here to here should go over the Atlantic, which is the expensive part of the internet. The expensive part of the internet is the transocean cables in general. Then, of course, ISP1 has his own cable or his own fraction of a cable for which it pays a huge amount of money. ISP3 also has a cable to Europe. Of course, if you are an internet service provider and you have a local presence only in one continent, you still need interconnections to the rest of the world. Or you need otherwise to be customer of other providers that have this interconnection. ISP3 could cheat and say, well, all traffic to C2, instead of using my red link, which costs me a fortune, I will send it to ISP1 as if it is local traffic. And then ISP1 will use his transatlantic link. Of course, ISP1 might not like to do this. So the goal of policy routing is to avoid this. So ISP1 agrees to carry over its links traffic to C1, for example, because C1 is a customer of ISP1. So if C3 sends a packet to C1, ISP1 will accept to carry it over the Atlantic if needed, but not to C2 because C2 is not a customer of ISP1. So the goal of policy routing is to enable those restrictions, put restrictions on where things go. Policy routing is typically implemented by filters in BGP. We said in BGP, a BGP router will choose the best route, and the best route might involve, for example, saying, I don't like this ISP. So how do we concretely implement those I don't like? Well, by filters. For example, filters might be in the simplest form, considered by simply refusing things. For example, ISP1 will have a list of all the routes it accepts to import, and similarly, the one it accepts to export. Imports means the route I will make visible to, if I import something, I will make it visible to my customer, and export is the information I give to others. For example, as a result of those rules, ISP1, this one, does not announce C3, this one, to ISP2. So ISP1 knows how to route to C3. It needs to know how to route to everyone. But it will not announce this to ISP2 because C3 is not a customer of ISP1. So ISP2 will have to learn it in a different way. And similarly, ISP1, ISP3 might give to ISP1 the information about C2 that it has learned from ISP2, so via a long link. This one will refuse to import it inside its network to avoid going this way. For example, to avoid going 2 times through the Atlantic. Typical cases are that customers announce all routes, announce all routes to their provider, and providers accept only routes of these customers, whereas the customer accepts all routes given by the provider. And shared cost peers screen very carefully which routes they announce. What exactly is done here, we don't really know. In fact, it's a business contract between 2 providers that are peers. You may decide that if you're strictly peers, which means there is no money exchange, I don't pay you and you don't pay me, typically we will do only this. We will announce and accept only to route to your customer and my customers, not to the customers of a third party. But of course, everything in between is possible. You may have an operator, for example, Swisscom, that connects to AT&T, and although AT&T is not providing a general transit service for Swisscom, it may accept to serve some destinations of Swisscom. For example, I don't know, New Zealand or a few other places that Swisscom does not have a correct agreement. It might decide to use the network of AT&T to go to this destination. This will be reflected in the routes that AT&T accepts or does not accept to import and to export to Swisscom. Voilà, what we have seen is at a very high level, at the level of clouds, what BGP is intended to do. Now the next phase, and this is the most less, or at least to me, the less intuitive one, is how a BGP router works. It's not intuitive, at least to me, when I saw that for the first time, because the intuition is we have hierarchical routing. We have two levels of routing, inside a domain and between domains. So when you have a hierarchy, you expect that you build a higher level, so that you would build nodes that represent the interconnection domain. And when you want to route between domains, you go to the transit points that would take care of routing between themselves. But that's not how it is done. BGP routers are routers inside a domain. They are not special external routers that would sit between domains. So that is because of this co-location of a router where BGP is just one additional routing protocol that you add into a router, that the thing is complex. Even worse, as we will see, we see lots of weird cases that are hard to understand unless we analyze things like we will do now. For example, we will see that very often you have BGP routers inside a domain that are not connected to any external peer, but they still run BGP. This is a bit paradoxical. In order to understand why, we need to dive a bit into how a BGP router works. The good news is that the model of a BGP router itself is specified by a standard. So we say exactly how it should work. First, as we said, BGP router uses TCP connection. Over this TCP connection, they have a heartbeat mechanism, so a keep alive mechanism, where they monitor that the other end is still alive and working. And if it's not, if the heartbeat fails, we will decide that the other end is dead, and all the routes that were originated by the other end will be deleted. Second, the BGP, unlike, that's a very big difference with what we've seen for RIP, BGP informs neighbors of only changes. It sends only the delta, additions and deletions. So if there is no change in the topology and in the reachability, which rarely happens, but if there would be no change, the only thing that BGP routers would send is keep alive. If a route is removed, then we explicitly send a withdrawal message. If a new route is added, we send an addition message. That's different from RIP, where RIP periodically resends the entire routing table. If a route is removed, then it's not in the new update, and we have seen that in RIP there is also route poisoning that is done. If a route is added, we simply add it in the update. If the update is the same as the previous, then we simply resend. Here it's different. So the idea is, of course, because BGP has a huge number of routes to transmit, routers that are at the core of the internet, like the AT&T or Sprint routers, or level 3, they have more than 500,000 route entries. So the complete table is more than 500,000. So this is, if they would resend periodically the entire table, they would resend 500,000 entries, which obviously you don't want to do. That's the first thing to remember. Now, here is the, perhaps I will show this on the figure. Here is the model of a router. So all of this is a BGP router. A BGP router has a number of routing information bases. So tables in which you copy routes. They are called ribs. We have a rib in RIP, but in RIP, the rib of RIP is practically the same as the routing table. Here in BGP, it's very different. In particular, BGP keeps a cache of all the inputs. It's called a rib in. So a router has typically several other BGP routers it's connected to, several other peers. And for every peer, it copies the last message it has received from these peers. A copy of all the last message, not only the last in time, but the last update relative to a given route. So for all routes that I've learned through a given peer, I have here a copy of the last received route. And then the way a BGP router works is first it applies the input processing, the import filter on this. As we have seen, it may decide that some of the routes it doesn't like, so it will still copy them to remember them, and then it will apply a filter. And everything that has been accepted is, in the model it says it's put in the local route base that has all acceptable routes. In practice, the local rib does not exist because all the acceptable routes are here, but mentally we can think there is a long list of all the routes that have not been excluded by the filter. And then you apply the BGP decision process. The BGP decision process for every destination will select one single route according to a priority list of criteria. So the important keyword is one route. So to each destination prefix that exists in this collection of inputs here, we will pick exactly one. And the one that is kept will be put into the routing table. The routing table is called the forwarding information base in principle, except if we don't do it, we'll talk a bit later. So here, the routing table exists outside of this. So in a router, you have all the BGP ribs and then the routing table, which is used for forwarding packets. So if BGP writes directly, it will write in the routing table only the best route chosen. And second, BGP will inform all the neighbors of its own choice. So it will send to all the neighbors the routes that it has kept here. And we'll also keep in a cache the last, for every destination, we'll keep a copy of the last one that was sent. The important thing here is that how are BGP routes propagated through a network? Well, they are propagated by BGP routers, but we see that a BGP router propagates only its best choice. A BGP router may be aware of several routes to a given destination, but it will not repeat to others those several routes. It will repeat only the best routes it knows. That's an important principle. What are the criteria it uses to compute what is the best route? Well, for this, it uses a number of attributes. There's a huge number of attributes, more than 100. We will not discuss them all. But we'll discuss the most commonly mentioned. A route, when we say a route in the context of BGP, it's something like a prefix, n, 128.178/15, for example, plus the sequence of the AS path. So that's two attributes. So a route has the destination, the sequence of AS path, plus a number of things that are used to choose in a priority list. So an attribute that is so-called well-known mandatory. Well-known, that means everybody should have this attribute, and it's mandatory. Everybody knows what this attribute means, and it's mandatory. That means every route has at least this, which is the next hop. We will discuss in a minute what this is. So those three things are the minimum you need in a BGP route: the destination prefix, the AS path, and the next hop. The next hop is the IP address of the external router to which we send the traffic to that destination. And then there's a large number of other attributes. We will mention 3 of them. Local pref, which is a priority. Multi-exit discriminator, which is another form of priority. And wait, which is used essentially by Cisco, is proprietary, which is another form of priority. We will discuss what all those priorities means. Then the decision process will apply by default this order of priorities. So the decision process has to select one route for every possible prefix. Not necessarily for every possible destination. There may be several prefixes that lead to the same destination. For example, we might have 128/8 or 128/178/15. Those 2 prefixes both lead to EPFL. But they are different routes. So different prefixes that overlap are considered different routes. But for every route, we need to keep only one. So among all the available routes that we have in the RIB-in, we apply this priority list. First, we check the weight, the highest weight. So in other words, the weight is a way to manually set the priorities. The weight is not transitive. That means it stays in this router. It is put by the input filter. I said that the input filter may decide to kill the routes we don't like. Perhaps if you're really serious about things, you always want to be cautious. I don't want to route through this guy because I don't like it. I don't like it because it costs me a lot, for example, in my transatlantic link. So I don't want to route through this. Instead of killing the announcements that come from this guy, I may simply give them a priority that will make them very undesirable. So that's one thing we can do. Then there is another priority, local pref, as we will see, that is handled differently. If we forget about those, here is the essential idea. First, we look at the shortest AS path. This is another priority that we'll look later. Then 4, we say eBGP is larger than iBGP, which means something we have learned from an eBGP peer. So if it's, remember all the things we are comparing, they are in different RIB-in. So some of the RIBs are connected to external peers, some are to internal peers. Something we've learned from the outside we prefer. We will see what's the effect of that. And last, the shortest path to the next hop that we will discuss in a second. The simplest way to understand what this means is to do a cartoon, an animation of a small example. So here is a small example with 2 domains, X and Y, and 4 routers that are running BGP. The routers R3, R4, R1, R2. Assume hypothetically I boot, which of course in reality never occurs at the scale of an entire router, but in the lab does. R3 sends to R1 a given message. So R3 knows that in the domain X there are 2 prefixes, 10.1 and 10.2. I'm using 10 domains, 10 dot something IP addresses. Usually it's not done because those are private addresses that usually we don't pass along, but that's just for simplicity here and to avoid using addresses that are used by someone else. So we see that R3 is connected to 10.1 directly and to 10.2 indirectly, but R3 is configured in a way that it announces to R1 all the routes that exist inside the domain. So it will announce those 2 things. Then this is what will be written in the adjacency RIB at R1. So we're focusing at R1. It will say, I have received this from R3. Here is the route, and I have at least the 3 attributes I mentioned, the network, the AS path, and the next hop. What is the next hop? The next hop is the IP address of the external point to which I should send traffic to go there. In this case, in many cases, not always, in many cases, it is the IP address of the external peer that has sent this information to me. So here it's 1112, which means if I have traffic to send, if I am R1, I have traffic to send to one of those two prefixes, I should send it to this one, at least if I have no other information. That's the use of the next hop. Now, of course, at this stage, what will R1 do? R1 will apply the decision process. There's no big thing to do. It has only one of each, so it will choose them. Then, if export policies don't ban it, it will inform all the other routers, which is here only R2. It will, of course, not inform R3 of something that comes from R3. It will inform R2 of those two routes here with the same next hop. So the next hop is not an IP address of R1, but is the external IP address, the attribute that was here that is copied here. Which means now R2 knows how to go to those two prefixes. Is R2 able to route a packet to those two prefixes? Well, we will see a bit later how the interaction play. But the first thing we have to notice is that the network that is at the boundary between two domains has to be treated as an internal network by both domains. Question?
Yes, is the second table sent from R1 to R2?
Yes, so we're focusing on R1. Everything is at R1. So this is the out table of R1. So this has been sent to R2, yes. So far so good. It's not so exciting. Okay. Now, sooner or later, the same thing has happened in R2. R2 has received from R4 similar things. And R2 has received, now we always focus on R1 here. So R1, in the second step, has received from R2 those two red announcements. So they are placed in the adjacency rib in, 10.1.16y. But the next hop is different now. The next hop is 2.2.2.1 because this has been learned from R4. R1 applies the decision process, which will be the best routes. 5 more seconds. And the correct answer is no. So the best routes will not change. We have to go to the decision process and remember the 6 cases. And the only case that will hit here is, because there is no weight, no attribute that we can choose from, but the first criterion we will see is this route learned from eBGP or iBGP? Is it learned from an external peer or from an internal peer? Here the red routes are learned from an internal peer. Therefore, they have less priority. Therefore, they will not be used. So the routes that will be installed at the routes that will be installed are those two here. Remember, however, router R1 will have the complete table that is here. So R1 knows that those routes exist, but he will not use them. Why do you think that R1 wants to keep all those things? Why do we keep a rib in and not just keep the thing here? Because that costs a lot of memory. I mean, a BGP router process has to have a rib in with all the routes copied. It has which one are preferred, but for many routes there may be many multiple instances. Why do we do this? Well, it is because it might happen, and it often happens, that there are changes. For example, this route might be lost. We might lose the link here between those two. If the link gets broken, then the R1 will immediately know that the other route is available. So it will immediately be able to know this new information. And we need this because BGP passes only changes in its own content. So if the link here fails, for R2 there is no change. So R2 will not send any new information to R1 because that link has failed. So R1 needs to remember the thing that R2 had sent before in case in the future it becomes the best available information. That's why it keeps it. The second thing to observe is what is the effect of these rules that we've seen? Why do we choose this, and what's the effect of choosing this? The effect of choosing this is that R1 will route everything to 10.1 and 10.2 directly to the outside. It will not route via R2. If R1 had accepted this route, for example, that means traffic to 10.1 or 10.2 would have gone through the other link here. So here, this is an example of what is called hot potato routing. The combined effect of these rules means that we will go as quickly as possible to the outside. If I have something to send to Y from X, I will send to the nearest exit point. I will leave my domain as much as possible. Like when you have a hot potato, you try to get rid of it as quickly as possible. We do a break and we resume in 13 minutes. Example, this one, where we have the same two autonomous systems, but in the top autonomous system, in X, there are now 3 BGP routers. The plain lines indicate physical connections, or at least layer 2 connections, and the dotted lines means iBGP TCP connections used for iBGP peering. In other words, R1 and R21 are one hop away from each other, as counted from RIP, for example. R21 and R22 are also directly connected to each other, and the dotted line between R1 and R22 simply means that there is a TCP connection, which follows perhaps the path via R21, for R1 and R22 to exchange their BGP information. Another difference here is that we assume that the announcements that are done by R3 and R4 are a bit different. Now, R3 announces only the directly attached route, 10.1, whereas R4 also, like R4, that announces also the directly attached route, which is the different one. So in other words, in the previous case, we had given the responsibility to all routers in Y to announce all routes of Y. In this case, we configure the injection of routes a bit differently, and we say every router is responsible for half of the domain. Here. Again, we focus on R1, and we look at what R1 will do. When it receives, for example, from R3, the first route, 10.116, with AS equal Y. Of course, here it puts it in the, assuming it accepts it, it's put in the rib in, and it's accepted because it's the only one, so it's the best. It's chosen by the decision process. And then it's forwarded to all interior peers, which are R21 and R22. So both R21 and R22 have this information now. Okay, we continue. Now we assume that R1 receives from R22, so the routers on the top right, this information, 10.2, next hop 2221. So next hop 2221 means it has been received from R22, who has learned this via R4. So in parallel, I'm not showing all messages. In parallel, things have happened at R22, and now R22 sends this information to R1. R1 will also accept it because it's the only one it has. This is a new prefix, 10.2. So it will accept it. And it will pass it along to no one. It will not, no new message will be forwarded. It will not be forwarded inside the domain because we don't repeat. The main rule of IBGP is we don't repeat inside the domain something we've learned internally. And it's also not passed to R3 because that would create a loop in the AS path. So one rule I have not mentioned but is obvious, you don't want to create loop in the sequence of AS path. So if you receive something that has AS path Y, you don't pass this information to a BGP router that is in the AS Y with the same label here. So nothing happens, it's kept locally, but it's not forwarded. Let's continue, and now assume that R1 received the similar messages from R21. Similarly, R21 has received the same message from R4, and we assume that this one comes after this one. What will happen to this one? Is it selected as the best route? What do you think? I close the poll in 5 seconds. Closing. And the correct answer is yes. Why? Well, this route, if we compare the different attributes, well, it doesn't have any of the priority attributes, so we don't consider them. So now I have to compare it to this one. They're both received from IBGP, so from that viewpoint they're equal. Then the next criterion that will count is what is the IGP distance. IGP, be careful, it's not at all the same as IBGP. IGP means the interior routing protocol. What's the distance inside the domain to the next hop? Now remember, the next hop has to be considered is typically an IP address of a network that crosses the boundary of the domain, but it's considered as an internal domain, as an internal prefix. So it's internal to both X and Y here. But here we are in X. What's the distance to this versus the distance to that? Well, the distance to 3 is 3.3.1 is 1, 2 hops, whereas the distance to the other one is 3 hops. Right. The dotted line is not a physical connection, it's only a TCP connection. So this is 2 hops away from self, from R1. This is 3 hops away, so this one is better. We will use also hot potato inside the domain. There's no reason to send it to something that's further away inside the domain, so we send to the nearest. That's again the hot potato rule. So the answer is this one will be, this one will be promoted. Oops, ça bouge dans tous les sens. This one will be promoted to the best route here. So several things to recap here. First, we have seen that the operation of BGP is rule-based. We write a number of rules and priority fields, and then we apply this and see what comes. Of course, when you define things by rules, sometimes you can be surprised. There can be undesired behavior. In other words, configuring BGP is not so easy. You have to do a number of rules to achieve your policy, but as you can imagine, when you have 500,000 prefixes and you're peering with 100 peers, for each of them you have different policy and different rules, you need to manage things carefully. So typically, you need an application for simulating the impact of all the rules you are using just to be able to do this here. In the lab, we will not run such application. We will have small networks, but you will see a number of configuration that can happen and how we can manage them. The second thing is that The default rules that are in BGP are always those of route to the nearest exit point. But of course, we have all those intermediate and supplementary priority fields that we can add to change this behavior. This is what we will see in a few more minutes. But before that, let me ask you another question. Here I'm showing two networks that are peers, ISP1 and ISP2. And assume I have some traffic that goes from customer 1 to customer 2. What do you think would be the normal path to be followed if we apply BGP? This one, that one, or both in parallel? I close in 5 seconds. And the correct answer is the second one. Whoops. Which is called hot potato routing. If we use the default configuration, if we don't supersede the default by putting weights or local pref or other priority fields, we will exit the domain as soon as possible, which has and this is very often what is done. And it has the interesting effect is that if we apply the same rule in the reverse direction, we will see that the path followed by the two packets in both directions are not the same. In other words, routing in the internet is likely to be asymmetric, which is probably not the case inside a domain. If we use RIP and we normally give the same weight, the same cost to links in both directions, might not be the case if we give with EIGRP, if we give costs that depend on traffic. But if we give static costs, they're probably the same in both directions, so routing will be symmetric. If the route you use in one direction is the same in the other direction with RIP. Here in the global internet, it's probably not the case. So you should not expect that routing is the same in the reverse direction. Asymmetry is the rule, it's not the exception here. Hot potato routing is typically done by default. Some ISPs do the converse. They would prefer to do cold potato routing if they believe they are better. For example, if hot potato routing means my costs, I try to save my costs as much as possible, so you do that if you want to avoid carrying transit traffic. Now, some operators say things differently. They say we are expensive, but we give a premium service. So if you use our network, you will get better service than if you use another network. In order to achieve this, such networks will try to keep the traffic inside their network as long as possible because they believe they have better links and better capacity. So ISP2, if that's the case, would not use the red path, but would try to go as long as possible inside its domain, which is assumed to be better than competitors. So both exist, right? Don't believe hot potato is the rule. But hot potato or cold potato can be both found, and therefore asymmetry is the rule. We have seen before different rules in the examples where different, in one case routers propagated all the routes that were in the domain, in another case only part of it. So how is that done? Well, there are zillion of options. What makes BGP very complex is that for practically everything, there are several ways to do it. So if you go into a network and you see how do you use BGP, there are lots of options that can be done for lots of points. So if you multiply all the options together, you probably have 1,000 different ways of running BGP. One of them is how to originate a route. Be careful here about the terminology. There are lots of words that in common English mean about the same. Originate, inject, redistribute, that all means approximately the same. In the context of routing protocols, we try to make a difference. I say we try because you always find papers and white papers and academic papers and user manuals that are not using those conventions. But if you look at good literature like Cisco white papers, they try to consistently use different words for three different things. The first thing is originate a route. That means how you bootstrap. Bootstrap means someone in the internet has to say that, if we look at one of the examples before, TED.1 exists and is in domain X. Right? This has to be originated somewhere. That's the bootstrapping process. Then what the rest of BGP does is propagate this by selecting the best and repeating it. But somebody needs to originate things. So the word for that is called originating. How do we originate? Then we can do it statically. So you can configure the router by saying to it explicitly, here is the list of routes you need to originate. In one of the software we'll use, it's the network command that does that. Then we can, instead of using a static configuration, we can redistribute. Redistribute is a term that has always the same meaning in the context of routing protocol. It means use an information that is already available in another configuration file, typically of another routing protocol. For example, redistribute connected means we pass the information of all the routers that are directly connected to this one. Of course, you do this or that, typically, you don't do both. So if you use this option, that means every BGP router is responsible for originating in the internet the network prefixes that are directly attached to it. If you do only this in your domain, it will work only if all routers run BGP. Because otherwise there will be prefixes that will never be originated by anybody. An alternative to this is redistributed from IGP. IGP, remember, is RIP or OSPF, is the intra-domain routing protocol. Redistribute from IGP means we tell this router to originate all the prefixes that, if RIP is the IGP, that RIP has learned. This might have been the case in the second example. When we saw example 1, we saw one BGP router in domain Y that was originating in the world all the prefixes that existed in Y. It could have done that either because we have statically, manually told him to do so, or because via RIP it has learned all the prefixes that exist in its domain and it is configured to redistribute, to originate with the redistribution method. The three methods exist, of course. If you use them concurrently, you have to understand the side effects and you have to make sure that all the things that you want to originate are correctly originated. Yes. Aggregation is a topic in BGP. Aggregation is at the heart of the way IP is configured, is designed. IP addresses are meant to be topological, and if I have a big domain, its IP prefix is assumed to be a prefix of the prefixes of its subdomains, right? So for example, 128.178 is a prefix that is common to all EPFL subnets. But it's not true that 128, for example, is a larger domain that contains EPFL. In fact, for IPv4, to a large extent, this is not true. IPv4 blocks of addresses are largely random. Not entirely, but largely random. For example, the IPv4 prefix of EPFL is not contiguous with the IPv4 prefixes of the other universities in Switzerland. As a result, Switch, when it propagates to the rest of the world all the prefixes of all the Swiss universities, has to give one prefix at least per university. It cannot aggregate them in one. Aggregating is desirable. Why is it desirable? Because if you're at the core of the internet, you need one entry for every prefix that exists in the world. So by aggregating, you can reduce this size If you don't aggregate, you have huge numbers. So today we have huge numbers because in IPv4 we cannot aggregate a lot. I mentioned 500,000, a bit more than that is the number we have today. And part of the reason for having so many is, for example, in the case of Swiss universities, every Swiss university gives one entry in all the routers of all the level 3 routers in the world, for example, all the backbone routers that exist in all backbone providers. Even though at the end ETH and EPFL are always routed via switch, but since they're not contiguous, we have to give different entries. We have already seen that the IPv6 prefixes are, because now first it was done after, so we are smarter, and second, they are much larger, so the IPv6 addresses of all Swiss universities are postfixes of the IPv6 prefix of switch. So for IPv6 routing, inside the global internet, the level 3 routers, for example, they have only one prefix for all of switch, not one per Swiss university. It may be that BGP domain receives prefixes from different domains and it can aggregate them, but each of them is not aggregate. For example, if EPFL would run BGP, then it could be that a peer somewhere learns from EPFL and from ETH their IPv6 prefixes, and then it could aggregate them into one single prefix. But it doesn't have to. So what we will discuss is what happens when and if we aggregate. Here I'm giving an example. BGP works for IPv4 and IPv6, so I'm showing sometimes IPv4 address, sometimes IPv6. Here is an example with 4 domains. AS3 has received 2 announcements. This prefix with AS path 2 now is the AS number, and that one. Now AS3 assume its decision process at one of the BGP routers has accepted both, and now in the export policy, in principle, it should try to aggregate as much as possible in order to be a good citizen. There's no benefit for this network to aggregate, but if it can, it should in order to be a good citizen. Now you will tell me, being a good citizen, how do we enforce that? Well, there is a repository, there is a website that counts all the prefixes that are advertised at all interconnection points and sees if some could be aggregated and they are not aggregated. Then you post them on a billboard saying this guy is bad, they don't aggregate. So we hope that by peer pressure this works, and it works to some extent. Now the question to you, can we aggregate this, and what is the aggregated prefix? Or we can't, or the aggregated prefix is something else. What do you think? Close the poll now. And of course, as usual, the majority is right. They can be aggregated because if you write them in binary, which is easy from EXA, you look only at the last digits of this and you see that they differ only by the last bit, which is here 0 and here which is 1. So the 47 bits of this are the same as, of those two. So this is the correct aggregated prefix. Now it's interesting to see what happens if you aggregate. How do you continue passing the information? So AS3 aggregates. Assume it does. Again, nothing will force AS3 to do it, but it should do it. What should it pass to AS4? Well, it will pass an information, well, AS path number 3, and then should it send 1 or 2? Because the 2 prefixes were in 2 different domains. Well, the answer of BGP is, if you do this, you give this notation, the curly bracket, which means it's an OR. So you will pass so this notation means the path to this domain is 3 and 1 or 2. Which is the only thing we can say because we've aggregated both. So we give the information to someone else. For example, AS4, when they will send it further, it will say it is path 4, 3, 1 or 2. By doing that, we have lost some information. It might be that some providers like 1 and do not like 2, in which case they're embarrassed here. That might be a reason for not aggregating, but the reason of reducing the table size is compelling, so in principle, we always try to aggregate. Now I am in AS4, so I say the decision process in AS4. This is an incorrect way of writing the decision process of a BGP router in AS4. If you want, imagine in AS4 you have only one BGP router. So this single BGP router receives those two announcements, this one and, oops, that one. 2001 BABA BB 47, AS path 312, BABA BBEF 48, AS path 2. No, sorry, this one, BABA BBEF 48, AS path, yeah, the same here. So AS4 receives those two announcements. Which one will be declared as best if we use only default configuration rules? And the question says, can the decision process designate both routes as best? I close in 5 seconds. And the majority says no, because we said we cannot choose two routes, but the answer is yes, they are two different routes. This route here is, whoops, Voilà. This route here is not the same as that one. Those are two different prefixes. So they are not, we don't have two competing routes for the same end, for the same destination. We have two different destinations. So both can be best if they are, if there's no other choice. So the answer is yes, it's possible to designate both as best, because they are two different destinations. Okay, now assume the decision process in AS4 designates both routes as best. Which path does a packet from AS4 to 2001 BABA BIP follow? So to this, a packet from here to there. So the black lines show physical connections, because those are external BGP links. So external BGP peerings must correspond to physical connections in general. I close now. And of course, we use the direct path, because here there are now two routes, and we will choose the most specific routes inside the routers, because we will use longest prefix match. Now assume the link AS2 to AS4 breaks. So this link breaks here. What are the sequence of events? Well, AS4 will detect that AS2 no longer responds to BGP keep alive messages. So all the routes that are in the adjacency rib-ins are declared invalid. The decision process will recompute the best routes. The decision process is triggered whenever there is a change in the rib-in, because it takes the best of all the rib-in. If they add or remove from the rib-in, the decision process is recomputed. Now, for this route, BEBF, which is this destination, then it will compute the best, but there is none, because the only one it had received was this one. So this route is deleted. The routing table entry will be removed. So in AS4, there is no longer a routing table entry for this. However, there is, from AS3, we had received the aggregated announcement, so there is a route to this aggregated prefix here. Right. So this will continue to work. AS4 will now send via AS3 and then to AS2. Right. Well, this is illustrating typical operation and how you have the interplay of aggregation. We've seen that AS3 has aggregated. AS4 has two routes, one aggregated, one non-aggregated. And there is typically value in keeping both. You could say AS4 should not have both. But yes, AS4 wants to keep both the aggregated and the non-aggregated. The non-aggregated gives it a shorter path that it may prefer. But it still keeps the other one because it gives a backup path that will still be operational whenever that one disappears. So those are the typical uses of aggregated and non-aggregated routes. Of course, AS4, when it passes along here, the information will probably aggregate all of this into one single. So it will not forward this prefix further. It should not, because there is no value in having it. AS4 should not aggregate inside its domain because it uses those different routes for different routing decisions. So there is value to AS4. Okay. Now there remains one other tricky thing to look up into BGP. We have seen how BGP works and how it forwards the routes. But what's the goal of all that stuff? I mean, why do we run BGP? At the end of the day, the goal of this is to write into the IP lookup table, into the forwarding table, which is sometimes called the route, which is often called the routing table. In the context of BGP, it's called the FIB, the forwarding information base. Often I call it the forwarding table. So the end of this process is to be able to route packets inside all routers of a given domain. And for this, we need to have an entry in the routing table. There are two possible ways to do it, again, that are called redistribution and injection. Redistribution is redistribution of BGP into IGP. That's the most natural method. You are a BGP router. Typically, in this assumption, we assume you stand at the boundary of your network. You've learned from the outside a number of prefixes. Now, it's natural to say, well, for RIP, I will do as if those prefixes were directly connected to me, perhaps with a very high cost, and then I will pass this information into RIP. So any router, any place inside my network will compute the shortest path to me. And if there is another BGP router that has computed also a path to this route, a different path, then with RIP we will compute the shortest path to one of the two. So packets will go to the nearest of the two BGP routers. This is achieved if we do redistribution. So redistribution means a BGP router passes into the routing protocol like RIP all the routes to all destinations that it has learned of by BGP, that it has kept as best by its decision process. And now it's up to the IGP, to RIP for example, to propagate this information internally in the network. It seems quite natural because it follows the concept of this hierarchy of networks, with two-level hierarchy. But in practice it's not done, at least certainly not with RIP, because with RIP, imagine you do this, you have a network, even if you're a big operator, you probably don't have more than 1,000 routers and a few thousand network prefixes. So RIP will work well and has been dimensioned to work with those a few thousand prefixes. Now, your external router, if you're a BGP router at the core of the internet, will have learned 500,000 prefix. If you inject 500,000 prefix into RIP, you'll have distance vector tables of 500,000 each. So they will blow up, it will not work. It will not work, and it's not even desirable to make it work. It will not work because nobody had envisioned to have networks that are so large with RIP. And second, it's not desirable because you're using RIP to pass information that is not local topology information of your network, is outside information. So you're misusing RIP, which is calculating shortest path, to pass information that is entirely external and is huge, much larger than that. So in practice, it's not worked. It's not done, at least with RIP or EIGRP. It doesn't work if you try to do it because the memory requirements are too large for what is anticipated for those things. It works with OSPF. OSPF has been designed with the idea to have huge databases. But remember, OSPF, which uses link state routing, is not propagating distance vectors, but is building a map of the entire network. So in this map, we can put all the prefixes that have been learned from the outside. We'll come back to OSPF a bit later. In practice, all operators I could speak to, I didn't find a single one that uses this one, though you find it in textbooks, and some people say with OSPF it's done. In practice, what is done is this method, injection. Injection means that the routes, injection means you simply put into the routing table the information that is in the forwarding, in the RIB that is inside BGP. Be careful, injection and redistribution seem to mean approximately the same thing. You have information on the left, you put it on the right, but they're very different here. Redistribution means you put into a routing protocol something that will follow its way and propagate using the routing protocol. Injection means you put it there and it will stay there. It will not propagate. Injection means inside this router, I look all the best routes that are chosen by BGP and I put them into the local routing table. There's a little caveat that we will see in a minute. So it's practically always done. Question? No, yawning. Let's see an example how this can work. So here's my 3-network example. I assume R5, where is R5? R5 is here. Advertise this prefix 18.1 to R6. R6 transmits this information to R2 via iBGP. And if we use redistribution, then R6 will inject 18.1 into RIP here inside this domain. R1, where R1? Yes. Now, if I am at R1, what will happen? Well, everything is as if R6 had said I am directly connected to 18.1. Of course, if we use RIP, it's hard to make it work, but we should give a higher cost. For example, a cost of 6 to 18.1. In OSPF, you have the concepts of very, very large costs, which are by giving a different type to the cost, so that we make sure they're always considered as large. So R6 will pretend it's directly connected to 18.1. The information will propagate to R1 and R2. So at R1, for example, we will know where to write for 18.1. We know we have to go towards R6. And similarly at R2. R2 will, of course, advertise the route also to R4 via eBGP. Now, if a packet comes here to 18.1, it will reach R2. At R2, there is a routing table entry that goes to R1 because this has been redistributed by IGP. From R1, we know we have to go to R6, and from R6, we know we have to go to 222 because we can use the next hop directly. So the routing will work inside this domain. I think we can skip this a bit. I think we can skip this. As I mentioned, this is not done in practice for the following reason, which are the number of route entries. It will simply blow up. And the convergence time is typically very large. And as I mentioned already, it's not desired because the thing that if there is a failure of a link inside a domain, you want this failure to be propagated as fast as possible using your interior routing protocol. but which is the goal of an interior routing protocol. Here, you will be embarrassed by carrying this 500,000 prefixes. Therefore, the alternative method of injection is often used. Now, with injection, I said, when we use injection, we put into the routing table the information we have learned from BGP. But what do we put into the routing table? In principle, in the routing table, we put the next hop, not in the next hop, not in the sense of BGP, but in the sense of the next router I have to send the packet. Now, the next hop in the sense of BGP is what we put in the routing table. However, it doesn't have the usual semantic, the usual meaning of the next router to which I send the packet. Because if you remember example like this one, the next hop for the route 18.1 is 222. Is this address here. So in this BGP router at R2, the next hop is 222, which is not the true next hop in the sense of the routing table. For the routing table, the next router I go to is R1. So we have a problem to solve. How is this problem solved? Well, in the simplest possible way, by doing what is called recursive table lookup. So routers that run BGP, and by default now any router, is allowed to put a next hop that is not on link. What does it mean? A next hop that is not on link is, for example, this one here. Oops. I want to go to 10.1. I put as next hop 222.63, which is this address here, because we have learned from BGP at R1 this prefix with this next hop. So I put it in the routing table as if it would be truly the next place to go. The interface is not available. Now, of course, if we just do this, it will not work. When a packet comes with destination that matches this line, I will read next hop this one. And normally what I do is I call ARP to find the MAC address that corresponds to this, and I send it to that. But that doesn't work. This is not on link with me. I cannot find the MAC address, and even if I find it, it's not useful. What can we do instead? Well, we can use the rule that says, if I go to the routing table and I find a next hop that is not on link with me, I am at router R1 here, then I try again. That's why it's called recursive. So if I find this as the next hop, I go again into the routing table, and hopefully in the routing table I will find how to go to 222.63, which is in that case going to 2233 via a given physical interface. So it's truly a true next hop here. And this is what is done for injection to work. Thank you very much. We stop for here. We stop for today. We will see next week how to